Right, so we are recording it now. Let's do a quick recap of lecture 19. So in the previous lecture, which was yesterday, we talked about the modified equation. So the motivation behind talking about this equation is because the truncation error analysis that we have been talking about is quite simplistic or naive. Now what may happen is that if we use the usual method of putting all the error terms on the right hand side, we might end up wrongly estimating the truncation error because some cancellation can occur which is not seen in the basic form of the equation if you simply apply Taylor series analysis. So what we do is what we did was we derived the modified equation. So we are doing this analysis for the 1D wave equation, but this analysis can be done for any equation that you want, any equation for any given discretization. So we use the upwind discretization, and after applying the Taylor series expansion about n comma I, we get an equation which looks like this equation number B. And again, this is the simplistic equation, and if you were to estimate the truncation error as order delta t and delta x, which are the leading error terms in the delta t and delta x terms, we could be wrong. In this case, we are not wrong. It is indeed order delta t and delta x, but we could be wrong. Okay. So for that, what we do is we have to derive the modified equation. So in the modified equation, we try to get rid of the time derivative terms on the right hand side. On the left hand side, we have the actual equation terms, so we will not touch them. We try to get rid of all the time derivative terms of phi on the right hand side. Now, of course, we cannot get rid of all of them. If we try to get rid of one, we end up generating higher order terms in that time. So that's okay. So as long as we are happy with a certain order, so let's say third order terms do not have a t in it. So there's no phi ttt or phi txx or phi ttx, then we are happy. So that's what we did in the tabular form. This is where we derived the modified equation, and the final equation that you have at the bottom is the modified equation, and you can see that it only has in terms of till third order, it only has pure x derivatives. There's no time derivative at all, either pure or mixed, up to third order. The higher order terms that you have here will have time derivatives. Okay, so today we will start with this modified equation. So we have learned how to derive it. Now let's look at it. Let's see what information it contains. So we told you yesterday that this equation is containing a tremendous amount of information. So let's see what that information is and how we can extract that. So that is where we'll start from today. So let me write the equation again. Plus some higher order terms. So here nu is the Courant number, which is u delta t by delta x. So if I was to use the upwind discretization for the 1D wave equation, I'll actually solve this equation. So we wanted to solve del phi by del t plus u del phi by del x equal to 0. But because we have made an approximation in the discrete form, we end up solving this equation, which has infinite number of terms, but we have only written terms till the third order of phi. Right? Is that clear? Well, I shouldn't say solved by the computer, that confuses us with a round of errors and so on. Solved by the upwind scheme. So let's look at the right hand side terms, which are the error terms. So let's look at the first term, which is, well, if you expand it, you get u delta x by 2 times phi xx, and you get a minus u delta x by 2 times nu times phi xx. So a nu is u delta t by delta x. If you multiply that by delta x, you get u delta u square delta t by 2 times phi xx. Correct? So we see that we have a delta x, we have a delta t. Now let's look at the other next term, which is this one. So this is giving us, there's a 2 nu squared. So nu squared contains, so nu squared is again delta t squared by delta x squared times u squared. So we get a minus u cubed, and then I get a delta t squared upon 3, right, times phi xxx, and then I have a plus, we have a u squared by 2 times delta x delta t times phi xx, and then we have another term which will be phi xxx times some coefficient which will have that multiplied by delta x squared, and then so on further. So what we are seeing is that the term phi xx, which is purely in derivative of x, has a term which contains order delta x and delta t. So this scheme is indeed, the truncation error in this case is order delta t comma delta x. So this is how we conclude. So the right hand side, you have to see what are the leading error terms on the right hand side after you have written the modified equation, after you have eliminated the time derivatives in phi. And the next term we have delta t squared, a mixed delta t delta x, and a delta x squared. So the leading error terms are still these and these. Okay, so this now we have concluded correctly that this is order delta t delta x, and this was the reason I was shying away from talking about deriving the truncation error for mixed derivative schemes. So simply 1D steady state, that was okay, but when you have this kind of a situation where you have time and space derivatives, then you have to write the modified equation to check if there is any cancellation. So I'll give you a homework. In fact, let's write it here, where you will indeed see some cancellation happening. So there are many examples possible. So let's write this one scheme. Okay, so for this scheme, which is called the lax scheme, now there are many schemes available. If you look at the book by Pletcher, they'll have plenty of schemes given to you, and each scheme's pros and cons will be provided. So there are lots of schemes. Our job is not to remember or to have an idea of how each scheme looks. So the basic one, the upwind, the first order upwind that we've been talking about, is something that you should definitely know. But all these other ones are, you'll get used to them if you start working in this field as a researcher, or you start using them in your projects or jobs. Otherwise, you should have an idea of this idea of upwinding, writing the modified equation and extracting information from this modified equation. Okay, so for this scheme, we have to show that the error, truncation error, is order delta t, comma delta x squared by delta t. So this ratio is only, it will only appear if you write the modified equation. Okay. Right, so that was one. The first thing is the truncation error information that you can extract from the modified equation. Well, I told you there's a lot more than that contained in the modified equation. So let's look at the equation again. So on the right hand side, if I had an equation which had a del phi by del t and it had a del 2 phi by del x2, does this term ring a bell? Isn't it a parabolic equation? Because parabolic equation has a del phi by del t. On the right hand side, it has a del 2 phi by del x2 times a coefficient. Now this time we also have a convective term. On the right hand side, the first term is something that you have a feel of. Except that this time this term has appeared in the error. But that is fine. I mean, ultimately the error, it's the behavior of the equation that we want to understand, that we are solving through the computer. Okay. So the first term on the right hand side is very much like your diffusion term. And we know that the coefficient of this diffusion term, which is called the diffusivity, cannot be negative. Diffusion coefficient is always, the alpha that we've been talking about is always positive number. Things diffuse out. Thermodynamically, you cannot have a negative diffusion. Things cannot, you cannot have things coming back and becoming whole together. Okay, so that diffusion is always positive, it spreads. So this coefficient of diffusion always has to be positive. So negative diffusion coefficient is fundamentally unstable. Computationally, physically, it's not correct. So I can very much with confidence say that the coefficient of the first term on the right hand side has to be positive. So that means u delta x by 2 times 1 minus nu has to be greater than 0, since positive diffusivity. So I'll say negative diffusivity is inherently unstable. Or physically impossible. Now, what does this condition tell us? Now, u is positive, that's the equation that we've been working with. Delta x is always a positive number, so that means 1 minus nu has to be greater than 0. So, what is that condition?
Velocity has to be positive.
No, nu is not velocity. Nu is Courant number. Huh? Velocity is positive, yes. So u is positive. So if u is positive and delta x is so u is positive is known. That was the equation we were working with. So we get a condition 1 minus nu is greater than 0. So that means nu is less than 1. And what condition is that? That's the CFL stability criteria. So that von Neumann analysis that we did to get this criteria, this is an alternate way. So modified equation contains the information about stability as well. And the same can be seen for parabolic equations as well. If you write the modified equation for that parabolic equation that we worked with, which was del phi by del t plus is equal to alpha times del 2 phi by del x2, you write the modified equation, you will get the stability criteria for that as well. Okay, so stability criteria is something that is contained in the modified equation as well. So we'll call this 2. Okay, so 1 was the truncation error information, and 2 is the stability. So let's add the stability part as well to this homework problem. So both of these you have to do using modified equation. Any questions? So delta t and delta x are our choice. They have nothing to do with the physics of the problem. So they are numerical parameters that we choose while solving the problem based on how much accuracy we want and so on. So in looking at the truncation error or looking at the modified equation, can I make this scheme more accurate by choosing special values for delta t and delta x? Look at the error term. Look at the term u delta x by 2 upon 1 minus nu times phi xx. Can I make this term 0 somehow? So that's how if I make this term 0, then the error order will be better.
Delta x equal to 0.
No, delta x equal to 0, then you don't have, you have infinite number of mesh points. They have to be finite.
Nu should tending to 1.
Nu should be equal to 1, right? So if nu is 1, what happens? The first term goes away. So that's a neutral stability condition. So I can live with that. Nu is less than 1 is always good. Nu equal to 1 is neutral stability. Nu greater than 1 is a problem, numerical issue. So if nu equal to 1, then what happens? And nu equal to 1 means u delta t by delta x equal to 1. So u is based on physics, whatever the velocity of the problem in the problem is. So I can choose delta t upon delta x is equal to 1 by u. So I can choose my delta t, and then delta x can be given by this condition that delta t by delta x is equal to 1 by u. So I get nu equal to 1. So my first term becomes 0. What about the second term? That is also 0. And you will see that all the terms on the right hand side will become 0 for nu equal to 1. That special choice of delta t and delta x, which gives my the new value equal to 1. So if I choose nu equal to 1, I will end up solving the exact equation, which is the equation I wanted to solve by using this upwind scheme. So the algorithms, finite difference algorithms that satisfy, that show this behavior are called to satisfy the shift condition. So this is called shift condition, where for a certain value of the parameter, I mean new in this case, the parameter that contains the stability information or the ratio of delta t and delta x or whatever in some ratio. So that allows us to choose a special value of delta t and delta x, uh, giving the exact equation that we're trying to solve. These algorithms are said to satisfy the shift condition. Now, this is for a very special case. I would rarely want to use nu equal to 1. 1 because for the stability, it's a neutral stability condition. It can or cannot work. And the other is that I might want to choose delta t and delta x values based on how much accuracy I want in space and time. Okay. So, but this is called shift condition. I'll not discuss any more about this in this case, but I'll give you a reading assignment to read from book. This is more on this shift condition and how that relates to this special problem. And in fact, this equation, 1D wave equation, shows the characteristics behavior. So if you have solved the wave equation in any of the courses, then you would know that there is wave travels in a certain direction. And these directions are called characteristics. So, I mean, you can actually solve this equation analytically. Okay, but this is beyond the scope of this course. I would not want to do that. I might give you that solution as a verification step in your lab, where you can compare the solution from the upwind scheme with the exact analytical solution. Okay, but the book has more detail if you want to read more on it. Right, so let's come to the next part, which is now we analyze the error terms. We analyze the behavior of the equation that we end up solving. Because see, we are not solving the exact equation, we are solving the modified equation. The modified equation contains higher order derivatives on the right hand side. So actually you are solving an equation which has a phi x x, a phi x x x and so on in it. So they will definitely have a different behavior from not having those terms on the right hand side. So you have sort of added a diffusion to your problem. Okay. So what we'll do now is start with a fresh page. So we are solving this equation del phi by del t plus u del phi by del x equal to, now we have u delta x by 2 times 1 minus nu times del 2 phi by del x2. And we have higher order terms, but I'll neglect those because these are the leading terms. So if I was to add this term with another higher order term, then the sum will mostly contain this first term. Okay, so now I'll remove that. Neglecting higher order terms in the error on the right hand side, you get this equation. So now what I want to do is I want to look at the behavior of the solution. And the reason I want to do that is because so this is for the first order upwind. There is also a way to write a second order upwind. Okay, so this is in the error. Let's write in the first order upwind scheme. Whatever scheme we have been talking about is first order upwind scheme. So first order means it's order delta t comma delta x. Without discussing how to do that, you can actually figure it out. It's not that difficult. We'll give it to you as a homework assignment problem. You can also have a second order upwind scheme. and this time you will have the leading error term will have del 3 phi by del x3. So we'll do something as we have been doing in to generate higher order schemes. We will do something to get rid of this first term. We'll have to include more terms in the discretization. So this is not the exact same. This discretization we've been talking about is first order upwind. If we were to use 2 upwind points rather than just 1 upwind point, okay, then we'll generate a scheme which will have a behavior which looks like this. So there will be some coefficient here. Let's call that coefficient as beta. Now this is again the leading error term. We'll have more terms, but they'll be of smaller error. So this beta will contain terms which will have order delta t squared, delta t delta x, and delta x squared. So this scheme will be second order accurate. Now there are different ways to generate the second order scheme, but this is how typically a scheme would look like. So when I solve this scheme, let's call this coefficient as alpha. So alpha will have all the information on the coefficients. So if I was to compare the solution behavior of a first order upwind, which looks like the first one, and a second order upwind, which looks like the second one, their solution will have actually very different behavior. Now the second one will be more accurate, definitely. That's the reason we are going for a second order upwind. But the errors in the solution will have a behavior, and I tell you what that means. The behavior will be very different of the two equations. So what we'll do now is, in this lecture, we'll talk about, well, there's not much time left. How did we finish this lecture very quickly? Okay, so I'll finish at 50 today, and then we'll continue. So first we'll analyze the behavior of the errors in the first order upwind scheme. So let's do that. So the exact equation we are solving is del phi by del t plus u del phi by del x equal to 0, where our x is in the whole real space. So the solution of this is phi as a function of x and t. So that is how the solution will be. It will be some function of x and t. So again we can use the idea of Fourier series. Now this time we are applying the idea of Fourier series on the solution, not the error. Remember that. Okay. So what we'll do is we'll try to write our phi as a function of x and t as the sum of infinite number of waves of different wave numbers. So let's say a kth wave number has a coefficient ak, which is a function of time, and we'll sum over all the wave numbers. And this sum is, we have infinite wave numbers or infinite frequencies, if you want to call it. Frequency typically is in time, wave number is in space. So this is how we exactly did for the error. In fact, for any mathematical function which is smooth enough, we can write this phi as a function of x and t is a summation of these infinite waves. Okay. So let's substitute that into the equation. And in fact, what we'll do is, let's consider only one Fourier mode. Let's not write the whole. So let's consider only one Fourier mode. And then we will, because the different Fourier modes are independent of each other, so we don't need to write the summation, it becomes a bit tedious. So substitute phi equal to just one Fourier mode ak e to the power of jkx. There's no delta x this time because we're talking about the actual function phi, not the error. So this has nothing to do with discretization. This is for the actual equation. So we have a del phi by del t term, so that becomes dak by dt, because a is a pure function of t, times e to the power of jkx plus u times del phi by del x. So a this time is a constant for this differentiation, and when you differentiate a to the power of jkx, you get a j times k out, and then you get e to the power of jkx, which is equal to 0. So e to the jkx will cancel out. Then I have, let's drop the k also for convenience for now. So we have dA upon A is equal to minus um, right, plus some constant. So we'll get a log of A, natural log of A is equal to minus juk t plus constant. Then I can write A as e to the power of minus jukt plus c. So this is times e to the power of c, which is some constant as well. So let's call this a naught. Okay, so this is the expression for a as a function of time. So now I'll write the function phi as a function of x and t, which was summation over all k values times a naught. Now the coefficient is different for different k waves, times e to the power of minus jukt. So this is coming from our, this is the expression for a, which we had written here, ak, and then we have e to the power of jkx. All right. So this is by using the idea Fourier analysis. You'll know why we are doing this. Now what we'll do is, we'll do the same exercise for the first order scheme, which has a right hand side which has a leading term in phi xx. So we'll do the same analysis. Let's give it a number. Okay, so let's call this A. And this is, by the way, homework for you. Whatever we have done, you just do it by starting with an equation which, rather than this, looks like A. So on the right hand side, it does not have a 0, it has alpha times del 2 phi by del x2. So this is phi exact. If you had could solve the exact equation. So this time we'll have phi numerical as a function of x and t. A equation is the first one. So this is A, this is B. So the modified equation with only the leading error term for the first order upwind scheme is equation number A. And the one which was for second order upwind, which has the leading error term as phi xxx, is the equation number B. So we are doing the analysis for equation number A. Right, so we repeat the same analysis for A this time, and what you see is the numerical phi in this case looks like this. Now let's compare these two. So what do you see? And this now I need 3 minutes. I want to finish this discussion now. So what do you see here? Is there anything that is different? E to the power of minus alpha k squared t. And if you were to plot this function where you know that alpha is a positive number, k square is positive, how will this function look? It's a decaying function, e to the power of minus c squared t. So it's a decaying function. So what this function is doing is, now that is the exact solution, the one above. So we should have a solution like that. But what happens is, for waves which have higher wave numbers, they tend to die. The information is dying very quickly. We don't want the information to decay or die. But that has appeared because of the diffusion term on the right hand side, which is appearing because of the error. So the first order upwind schemes are highly diffusive schemes. And that is what we see from this. So I will write it down and then it will be. So I'll reinforce that idea again in the next lecture as well. So we'll write Fourier modes with a higher k value decay faster. Now remember, let's actually show it to you graphically. So let's say we have a solution which looks like this. The solution could be anything, but I'm just so let's say the solution actually looked like this. For some reason. Now this solution, if you were to write as a Fourier series, would contain two prominent k values. One is this larger wave number, and the other is one is the smaller wave number or the larger wavelength, and the other is the larger wave number, which is this one. Of course, this one has a smaller amplitude. Okay? So I would rather write it as a smaller amplitude, but the frequency would mimic the frequency of this wave. So if I was to add, and you can play around with on MATLAB or Python with this, if you want to get a good feel of functions and frequencies, and there used to be a dedicated course on this earlier, but now that's not there anymore. So if you add these two waves, you will get this kind of a wave. And if the solution was like this, it would be a sum of these two. And if you use a first order upwind scheme, what would happen is, for the larger wave numbers, they'll tend to die very quickly. So if you solve it for some number of time steps, you'll actually only get this as a solution. The higher wave number will actually die out. So what this first order upwind scheme is doing is, it is smoothening the solution, because the sharpness in the solution, sharpness mathematically means a higher frequency or a higher wave number, right? If you have a sharp function, a sudden step, that step contains a very large, infinitely large frequency. So the larger the k value, the faster the information dies. So these first order upwind schemes, they tend to smoothen the solution. Wherever you see the sharp changes or something, they'll get smoothened out. It's a very good way, it's a very good operator to smooth things, by the way. So anyways, so this is where we'll stop, and I'll discuss this idea in a slightly more detail. So these errors are called diffusion or diffusive errors.